All right. Hello, everyone. Thanks for listening to our session today. My name is Lou, and I'm Senior Manager of Data Science and Machine Learning team at Berkeley. I'm excited to be presenting our work at Data AI Summit. Today, we are going to talk about the context-aware classical recommendation services we built at Berkeley. I'll start with the use case introduction, and then talk about newly developed DX models in details. And then Kai from Intel will talk about AI and big data, and how we build our distributed training pipeline using Rails. Our full recommendation use case takes place in the drivethru environment. So for some of you don't know, drivethru is a type of food ordering services that allows customer to order the food without leaving their car. Drivethru becomes especially important during the current global pandemic environment because it's very easy to enforce a social distance without asking customer to leave their car. So this is a typical drive-through process where the process starts with a guest arrives at drive-through, and then typically they first check the outdoor digital menu board, see if there's something they like, and then they start ordering process by telling the cashier to enter some orders. And then they normally check the menu board again to make sure the order is correct and see if there's something else they want to order. So this process typically iterates a few times until the guests find all the items they want to order in the drive-thru, and then the process concludes. So how can we add in the recommendation into this process? So this is what we think, right? So when the guest first looking at the menu board, there's opportunity, right, for us to use machine learning-based services to show some recommended items to the guest, right? As guests continuing during the ordering process, our recommended services needs to react, right, to what guests already ordered and continue refreshing the recommendation items, right, to make sure it captures the guest interest in real time. And yeah, that's our full recommendation use case. So how is that different from e-commerce, right? A traditional e-commerce recommendation use case. What are some unique challenges in our use case? So first challenge here is because it's happens in offline environment, and they're just very limited in terms of user identifier, right? Guest stays in a car. There are certain technologies like license plate recognition or scanner able to identify the guest, but they all have their own limitations, right? So in our case, we need to build a solution can work even without user identifier. And also, there's unique challenges here related to the food items, right? So in our recommendation use case, we need to consider the same session for compatibilities. So just give some example, right? If you order, if you buy some games on the e-commerce website, it's naturally recommendation system recommending some other games, right? But because this is food and human only have limited appetite, right? So if you order things like soft drinks, right, it's not likely order another soft drink during the same order. So that's some unique challenges in our use case. And also we have to consider other variables in our use case, right? So there are things like locations, the weather, the time. They all play an important role when guests ordering food. So our model needs to be able to consider all those, right? And also deployment challenges. We need to be able to deploy the solutions across all the working restaurants across the world, and not only the locations with good network connections, right? So our deployment solution also needs to be very flexible. So we kind of break down solution from two parts, right? So the model part and the deployment architecture part, right? So for the model part, given by our unique use case, we think we need to develop a session-based recommendation models, right, to solve this, because a session-based able to react, right, during the same session behavior. So it's not that relying on the user identifier. It can even work without user identifier. And also our model needs to be able to take complex context feature into considerations, right? So without the user identifier, the only thing model has is the same session behavior information and the context information. So it needs to be able to capture both of those, right? And from the deployment architecture perspective, our model needs to be able to deploy anywhere, right? So both edge and the cloud. So we kind of leverage the Docker container registry, right, to allows the same recommendation services, right, running in any environment with a Docker install. Let's talk about our newly developed transformer cross-transform model. So we built this new recommendation model called a transformer cross transformer, also TXT, right, to solve our full recommendation space. It contains three main components. The sequence transformer part, where it takes item order sequence as input and feed into a transformer block to learn order sequence and representation. And the context transformer part, where it takes all the context features as input and feed into transformer block to learn the context feature representation. And also the latent cross part, where we conduct element-wise product for both transformer latent output to join and train our recommendation model. So we gain inspiration, right, to build this model mainly from Google's latent cross paper. So Google discovered the context feature is very important, right, when doing recommendation services. And traditional ways of adding context features through concatenation, it has lots of limitations. So Google then built this RN latent cross model where it contains an RN part and a latent cross part to infuse the context features into RN output state optimally. The difference between RN latent cross and our TXT model, first is we replace RN with transformer architecture. So it can achieve faster parallel training speed when doing big data model training. And second, we also introduced a separate transformer block, right, to capture the complicated interactions of different context features. So the model can learn a better context feature representation when there are multiple context features being presented. During the offline evaluation process, right, we benchmark TXT model against a few other models. Aside from the RN latent cross, we also compared with RN model, right, where it doesn't have the context feature as input. And the variation of the item filtering model with the input of with the context or features input. So this one doesn't have the sequence information. Result shows TXT model achieve the lowest cross entropy loss during the training, and also have the highest top 3 accuracy among all the other models. During the online A/B testing, due to a lot more complex model architecture, TXT model does show slightly slower average inference speed, right, compared to unrelated cross, but only by a little bit. Doesn't really affect our user experience when in the production. So that part is fine. On the other side, right, the result also shows TXT model has a much better conversion rate, right? Also the add-on sales comparing to the control group running the unrelated cross model. So the last part I want to talk about is the model training architecture. So previously we were using a separate young cluster and a GPU cluster to train our model, right? Where the young cluster is mainly running the Spark job to do the data processing, and the GPU cluster is running the MXNet pool, right, to train our deep learning model. And the limitation with this process is that there are two different clusters, right? And multiple data pipelines needs to be properly maintained in the production. Also, it takes a very long time, right? As our data size grows, for the data to be transferred between our HDFS and our young cluster and our GPU cluster. So that's kind of the limitation. And then by working with Intel, right, we kind of developed this a new unified model training pipelines, right, where everything happens inside the young cluster. So the same cluster, we do the Spark data processing. We also leverage the same cluster to do distributed model training using MXNet and Ray. Kai will talk the Ray on Spark part in a little more details in the following section.
Okay, thanks Lou for sharing the recommendation use case at Burger King and the TXT model architecture for context-aware recommendation. Since Burger King processes enormous gas transaction data on their big data clusters, it would be essential to build a unified system for the entire recommendation pipeline. So in the remaining part of this session, I will elaborate how we use Ray on Apache Spark to implement the distributed training pipeline for the TXT model. First of all, I will briefly introduce the work that Intel has done this year in enabling the latest AI technologies on big data. In 2016, we open sourced our first project named BigDL, which is a distributed deep learning framework directly built on top of Apache Spark. Deep learning applications written in BigDL are standard Spark applications and therefore can directly run on existing Hadoop or Spark clusters without modifications to the cluster. We have done lots of optimization so that BigDL can achieve both outstanding performance and good scalability on CPU clusters. Later in 2018, we further open sourced Analytics, a unified data analytics and AI platform for distributed TensorFlow, Keras, and PyTorch. With Analytics, TensorFlow or PyTorch users can seamlessly scale their AI workloads on big clusters for their production data. We provide high-level machine learning workflows in Analytics, including cluster serving and AutoML to automate the process of building large-scale AI applications. There are a bunch of built-in models and out-of-box solutions in Analytics for many common fields, including recommendation, time series forecasting, computer vision, natural language processing, etc. Recently, we developed a sub-project in Analytics called Project Orca, and Project Orca is particularly designed to easily scale out single-node Python AI applications or notebooks across large clusters by providing data parallel pre-processing for common Python AI libraries and scikit-learn style APIs for distributed training and inference. So we use the distributed MXNet training support in Project Orca for Burger King's recommendation system, which is implemented based on Ray and Spark. Also, in case some of you may not be familiar with Ray, I will talk about Ray for a little bit before I proceed. So Ray is a fast and simple framework open sourced by UC Berkeley Rice Lab to easily build and run emerging AI applications in a distributed fashion. So Ray core provides simple primitives and a friendly interface to help users easily achieve parallelism with remote functions and actors. Ray is packaged with several high-level libraries built on top of Ray core to accelerate machine learning workloads. For example, Ray-Tune can be used for large-scale experiment execution and parameter tuning. ILLib provides a unified interface for a variety of scalable deep reinforcement learning applications. So the third one, RaySGD, is our focus today. RaySGD implements wrappers around TensorFlow or PyTorch to ease the deployment of data parallel distributed training. If users want to directly use the native distributed modules of TensorFlow or PyTorch, they might go through the complicated setup steps in the production environment. So the RaySGD can help to relieve the deployment efforts to some extent. So we adopt the design and idea of RaySGD for MXNet, and we have done some further work to make our implementation best fit the Spark data processing pipeline. Okay, so let's go into the implementation details of the distributed training pipeline on big data. We developed Ray on Spark to seamlessly integrate Ray applications into Spark data processing pipelines. So as the name indicates, Ray on Spark can run Ray on top of PySpark on Burger King's Yarn cluster. So first of all, for the environment preparation, we leverage CondaPack and Yarn distributed cache to automatically package and distribute all the Python dependencies on the driver node across the cluster at runtime so that users don't need to install them on all nodes beforehand, and the cluster environment remains clean after the program's finish. So in the Spark setting, as we all know, a Spark context is created on the driver node, and Spark is used by Burger King to load data and perform data cleaning, ETL, and pre-processing steps. And afterwards, Ray on Spark would create a Ray context object on the Spark driver as well. And the Ray context would utilize the existing Spark context to automatically launch Spark processes alongside Spark executors under the same cluster. Additionally, we can see in the figure that array manager would be created within each Spark executor to automatically shut down the array processes and release the corresponding resources after the array applications exit. Similar to RaySGD, we implement a lightweight wrapper layer around the native MXNet modules to help handle the distributed settings of a distributed MXNet training on the young cluster. So in our implementation, MXNet workers and parameter servers all run as Ray actors, and they communicate with each other through the distributed key value store natively provided by MXNet. So in our implementation, as you can see in the figure, we have Spark and Ray in the same cluster, and therefore Spark in-memory IDDs or data frames can be streamed into Ray's Plasma object store, and each MXNet worker can take the data partition of the Spark IDD from its local Plasma object store for model training. So for the coding part, we provide, Project Orca provides a scikit-learn style estimator API for distributed MXNet training based on Ray on Spark. So, but for users, actually, they do not need to know much about the details of Ray on Spark. They just need to import the corresponding packages in Project Orca and coordinate Orca context for the cluster setup. So when you coordinate Orca context, you specify the cluster mode to be young, and you can also specify the amount of resources to be allocated for your application. For example, the number of nodes to use in the cluster, the number of cores, and the amount of memory per node to use, etc. So in this Orca context, would prepare the runtime Python environment and launch the Spark and Ray cluster on YARN for you. So after creating the Spark context, you can use the created Spark context to do data processing using Spark, and finally you can get the Spark IDDs for training and validation. So the third step is to create the estimator for MXNet in Project Orca. So when you create the estimator, in the train config, you can specify the number of MXNets workers or parameter servers to launch. The code modifications and learning efforts should be minimum if you use Project Orca to scale out single node MXNet training script to large clusters. Since, as you can see in the code, you can directly input the model loss matrix defined in pure MXNet when initiating the MXNet estimator. So here in our use case, we input the TXT model defined in MXNet. And since our recommendation use case is next item prediction problem, we use the softmax cross entropy loss, and we choose top 1, top 3 accuracy as the matrix. So invoking estimator.fit would launch the distributed MXNet training across the underlying YARN cluster, given the Spark processed RDDs and the number of epochs and the batch size for training. So that's pretty much the code you need to write for the distributed MXNet training pipeline. So it should be straightforward, and such distributed training runs on exactly the same cluster where the data is stored and processed. So there is no extra data transfer needed. Previously, as Lou mentioned, when they use a separate GPU cluster for model training, nearly 20% of the total time is spent on the data transfer between two separate clusters, which is quite expensive. So after switching to the solution provided by Project Orca, in Analytics Zoo, the entire pipeline becomes more efficient, scalable, and easier to maintain since it only needs a single cluster, and there's no extra labor needed to maintain a separate cluster. So Burger King has successfully deployed the pipeline into their production environment to serve the customers. Okay, so here comes to the end of this session. And as a wrap up, in this session, we talk about the joint work of Burger King and Intel to build an end-to-end context-aware fast recommendation system using Ray on Spark. So we have released a paper and a blog for our cooperation with the links shown here, and you may take a look at it later. And if you want to know more about the technical details of Rayon Spark, we have a previous session in the past Spark AI Summit this June in this year, and which particularly talks about implementation details, and you may take a look. So if you want to know more information about Analytics Zoo, you can visit our GitHub page. And I think that the other functionalities of Analytics Zoo would be useful to your work as well. So if you have a GitHub account, don't hesitate to start our project Analytics Zoo on the GitHub page so that you can find us whenever you need, and we can give you timely help and support. Also, we are now actively working with other industrial customers for more use cases with Rayon Spark, and we will be glad to share our progress in future chances. Okay, that's pretty much what I want to talk today, and feel free to raise questions if any. And thank you for attending this session, and hope that what we have talked about could arouse attention. Thank you so much and have a good day.